Hello, guys. Very excited to be here. I hope everyone can hear me well. So my name is Ashot, but you can call me Ash. Consider friends. I think I was at one of those. Oh, sorry. A lot of videos here. I didn't expect that. So I think I attended some of the events maybe like 4 years ago. This is maybe the last time I was giving public talks in the Bay Area. It's true that I'm mostly focusing on low-level coding, but we do a considerable amount of Python as well. And it's been like this situation in the industry where people just use low-level languages for fast stuff. But then once you implement it, you actually want it to be usable. You want people to take advantage of your software. So that's where Python kicks in. So for everything that we build, we design Python layers on top of it. I've been doing it for a big part of the last 15 to 20 years. And for some part of those 15 years, for the last 7.5 years, I'm building a company called Unum. So today we'll be talking about the complexity of building up software. Most of you start in Python. Many of you will not finish in Python. Many of you will end up using libraries that pull all kinds of software from beneath. The overall idea is most times that we want to have software that we write once, and it runs really well on no matter how big of a machine we take. So if you take a machine that is 10 times more powerful, you want your software to run 10 times faster. Or if you take a machine with 10 times as many SSDs, you want your database to be able to address all of the same space, and the throughput would be 10 times larger. In reality, this is not the case. So there's like two branches of computer science that people forget about once they finish the university oftentimes. So the first part is, how do we take an algorithm that is perfectly fine and then spoil it once we try to make it work on parallel hardware? So this is the kind of work that is best categorized by companies that build parallel hardware because they want the software to run properly on it. And the second category is external memory algorithms. How do we design algorithms and software in general that performs well once we cannot fit it into random access memory? So from my potentially short experience, once you take a Python program and you rewrite it into native language, systems design language, you manually control the memory, you avoid too many objects and temporary objects, you can get 40x performance improvement even on a single CPU core. And then once you design a GPU version, you can go 500 times faster. And then the second line of external memory algorithms, imagine a server, a classical server can easily have like a terabyte of RAM today. And then at the same time, it would have like 100 terabytes of SSD storage if you are talking about really beefy hardware. So you can get to data sets that are 50 times larger, 100 times larger. And the holy grail of all of this is to combine the two approaches to actually end up working with parallel algorithms in external memory. This is kind of my big dream with what I studied 7.5 years ago. And I have a really long talk about this whole thing. So I gave this talk at PyData last year. You can go visit the website, YouTube, and just check it out. Today we'll cut it short. And we'll talk about like the two core parts of it. The first one is about Rapids. It's a framework by NVIDIA. And I guess it's a common practice in the Bay Area to tell everyone that you don't own the stock of the company that you really love. So this is the case here. I don't have any NVIDIA stocks, but their software is amazing. And one of those software packages is Rapids. The second part is about my company, about Unum. And we kind of take two different parts of this problem. So NVIDIA would focus on compute-bound problems, and we would focus on I/O-bound problems. So whenever I start talking about software, I prefer people to actually understand what kind of hardware they would be dealing with in the first place. So this slide is a kind of a counterexample because it says 10 Mellanox switches. It's 10 Mellanox NICs, networking cards. So this is an example of a server that people commonly use for AI training. Two sockets, essentially two CPUs, 64 cores on each one of them, 8 GPUs, very powerful, and 30 terabytes of NVMe storage. And then once you start using like packages in Python to address all of this machinery, you generally have the three first classical choices. You're working with linear algebra, you're working with matrices, you end up using NumPy. Everyone knows it. You start working with tables, you take Pandas. You start working with graphs, you take NetworkX. And the ecosystem in Python is very mature. But what people sometimes forget is that every one of those libraries has alternatives that you can always use to actually scale up your solution. For matrices, probably the only major thing one can suggest is CuPy, which is NVIDIA's distribution of their matrix multiplication library. For tables, there are a few more options. I'll name only 3, but there's a lot more. So there's Modin, which is kind of trying to port some of the Python code into like native languages and then combine it into a more advanced, efficient solution, mostly for CPUs. There is cuDF, which from name you can all guess which company is building. And then there's Dask-based solutions and a bunch of other potentially rate-based solutions, which would take this efficient, vertically scalable solution and make it horizontally scalable. And then for graphs, there are packages like RetworkX and cuGraph again. So RetworkX is a fully open source rewrite in Rust. Not my favorite, if I'm honest, but we'll get back to it. So I could have scared you a little bit with like all those compiled languages and like native space. But in reality, we can do a lot of stuff really fast without ever leaving Python. So if we build up a table like this, what kind of versions of software we have, like for all kinds of platforms, there's nothing new here. But let's dive into NumPy specifically. So NumPy in reality is mostly a Python face for what is already a native library. So there's the standard that existed for the last 40, 50 years, which is called BLAS, basically Linear Algebra subroutines. And every single hardware vendor, whenever they produce a new piece of hardware, ships a version of this library called BLAS. The point of BLAS is to define a few dozen essential operations, potentially even over 100, that they split into 3 levels: vector-vector operations, vector matrix operations, and matrix-matrix operations. And the beauty is that whenever you take NumPy, you are not taking one library. NumPy actually comes in all kinds of distributions with different versions of BLAS. It just depends on how exactly you configure your virtual environment, how exactly you pull the NumPy package, and what kind of details you specify. But you can easily get NumPy with Bliss, with OpenBLAS, with Intel MKL, which is the math kernel library, or with CuPy even potentially as a backend. So on the left side is like a few different use cases. Here we compute the moving average, which is probably the most complicated one of those functions, a total of 3 lines. Then there's Pearson correlation, fast Fourier transforms, matrix multiplication, SVD, flat sorting, medians, and summation. All those functions are very different, but I didn't have to change a single line or a single character for this to run on different kinds of hardware and with different versions of BLAS. And to give you a perspective of like how wide the gap in the underlying hardware can be, so on the right side, we have the GraphCore chip. We use some of those chips for AI training in my company. It has a lot of SRAM, 60 billion transistors, but it's tiny. So it's the size of NVIDIA GPU chips, essentially. On the left side, we have Cerebras chip, which is like a wafer scale computing stuff. They have 2.6 trillion transistors. And if you link it to the proper version of BLAS, NumPy would still work on this kind of hardware as well. So with CuPy, it was a bit of a different story. So we had to swap a few things. So there are very minor, subtle changes. A couple of functions here and there do not support the D-type argument. In some cases, the strategy in which they cast integers differs. And once you try your test toy example, you may not immediately spot the difference. But once you're loading in like a really large system, you kind of see those details popping up here and there. And then probably the most noticeable thing is synchronization. So the way it's organized beneath is that CUDA and NVIDIA driver beneath organizes a queue of different kernels that operate one after another. So essentially, you need to synchronize some of those operations within the queue to make sure that they're completed by the time you want to finish the operation. So it's all good and nice, but is it worth it? I think it is, especially on large problems. So the top rows contain stuff like singular vector decomposition and the numbers for that. So we take 2 matrices, or let's say we take just one matrix that is 16,000 by 16,000. And it's kind of obvious that on a lot of matrix-oriented operations would get speedups. So GPUs are notoriously good at multiplying matrices. And for GEM, which is the general matrix multiplication kernel, we get a 23x performance improvement compared to a much more expensive, energy-consuming 64-core Zen 2 liquid-cooled CPU. So essentially, you take a GPU that is $1,000, $1,500 worth, and a CPU that is $6,000 worth, and your GPU ends up being 25 times faster. Pretty good. But the stuff that people often forget about is that they are designed for a lot more than just matrix multiplications. So the bottom rows would contain operations like sorting, which is generally considered like to be like this out of order thing. And people would oftentimes use algorithms like quicksort on the CPU side. The GPU side will be designed in a different way. Oftentimes it will be using radix sort. So the numbers may only be applicable for, let's say, trivial types, like an array of numbers, but not necessarily an array of objects. But we still get 1000x performance improvement, which is amazing, if you ask me. So in reality, we're talking not just about libraries, but about entire ecosystems. And in case of NVIDIA, the 3 projects that are the most known are CuPy, cuDF, and cuGraph, but they are not the only ones. And if you have like some shared representation, like Apache Arrow buffers, you can actually exchange information between those libraries and every other library that I've just mentioned. So looking at NetworkX and working with graphs, potentially like most sparser problems, I've also added iGraph and Snap. Snap is the library from Stanford. iGraph is another open source library. As you see, they're not always feature complete, and their API is not fully identical. But even on graph-like problems, we can get performance boost up to like 1,300 in the bottom row. So the layout would be the attempt to draw a graph on a 2D surface. So it's a force-based algorithm for graph rendering. And then the same translates into Pandas, which is probably the most used library out of all 3. So there's this benchmark that everyone in the database community knows. It's the New York Taxi Rides dataset. It's about 2 billion rows. It has both categorical and numeric values. You can take the whole dataset, and it's pretty large, but if you want to fit it into a GPU memory, it's better to take only part of it. So we took chunks that are up to 2 gigabytes in size. We run them against the basic Pandas, and I have to put a disclaimer here because those numbers are from before Pandas 2.0. We get 60x performance improvements. So Pandas 2.0 brings Arrow, Apache Arrow, as its first like native representation internally, so we can get a lot of performance boosts essentially for free just by upgrading. So in reality, there's like this entire ecosystem of accelerated libraries that focus on compute. Those would be Modin, RetworkX, NumPy, Dask, and Ray. But there are a few things to consider once you start using them. One of the major things is that you have to treat your types really accurately. So whenever you pass anything like from one part of your Python application to another, make sure that it's using native types, because if it's not, the kernel beneath may end up working, but the performance will be a lot worse than what you expect. And a major problem that exists here between like Python native implementations and native languages is that using objects like lists is not really good for the underlying implementation because there is no locality. Objects are not stored one after another. So you have to run throughout the memory and chase a lot of pointers, making sure that the software works well. So the second problem that we see a lot is that people abuse strings. So whenever they can use categorical data, like for stuff like dates or enums, they still prefer to use strings. This doesn't work on parallel hardware well, because parallel hardware is oftentimes designed with very tiny cores. Those cores would not have any major logic on them, including branch predictor. And most of the things that you will be doing with strings would include running through a string, comparing character by character, and the branch predictor will be dying out there. So you don't want to do that. You want to treat your hardware well. And then the last part of this series is how people choose the representations before they pass here, like to the underlying package. So when we talk about graphs, the problem becomes a lot more evident. It's essentially about choosing between dense and sparse representations. So the dense representations would work really well. They're easy to address. Sparse representations are really hard to address. And you end up with all kinds of memory-bound and IO-bound problems that we'll talk about here. So a few years ago, when I started working on this like efficient data lake thing, there was this keyword that was just spreading, HTAP, hybrid transaction analytical processing. It's about our attempts to join OLTP and OLAP workloads that happen mostly in databases, but this is about broader analytics. So if you do a lot of IO optimizations, you can reduce the latency of any kind of software that runs in modern data lakes. And then if you use parallel hardware, you can achieve higher throughput. So we started working on replacing pieces of infrastructure bit by bit. And we started with a project that is called uStore now. So you can find it on our GitHub. This QR code will bring you there. So its idea is pretty simple. Can we build up a tiny database that would be embedded so we don't have to pay the networking costs that would store all kinds of data internally? So in the last couple of years, there's been like a few hundred new database companies. Almost all of them are built up on what is called RocksDB, which is like a very commonly used key value store. So we thought, just like there is BLAS for basic linear algebra subroutines, that was kind of the foundation of all the compute in the last decades, I thought we need a shared representation for IO operations and for key value stores as well. And if every single one of the database companies decides to build up on top of a key value store instead of building their own internal stack fully integrated, then we should have a good interface for the key value store. So we build up a series of C99 headers, which is like a very thin, very basic, very old school layer in between the underlying implementation and whatever language you want to bring on top. And the first language of choice for us is Python, because the rest of the data processing ecosystem is written in it. So we built up a C layer, which is like a binding. It can serve and work both on top of RocksDB, LevelDB, any in-memory key value store, any persistent key value store, including the ones that we have internally. And the idea is to add all kinds of logic for specific data types on top of it. So if you want to work with data frames, you can put data frames into RocksDB. If you want to work with graphs, you can put them into RocksDB, and you'll have this Python layer that will look exactly the same way as the libraries that you already love. So let's say NVIDIA took Pandas and accelerated it on GPUs, and we took Pandas and expanded it into external memory. And the same way with graphs. So instead of taking SQL or any kind of other intermediate representation, you immediately get the binary interface. And for us, the idea was that we needed our storage solution to support all kinds of operations that are not really very common to most databases. So for example, we love to build our AI training pipelines end to end. Part of it is that generally when you train AI, you have a thing called data loader, which is responsible for sampling the batches within every epoch. So most of the people I know work with relatively small data sets, small being less than a terabyte in size. And we prefer to work with data sets that are 100 terabyte plus on every one of our machines. And if you work with data sets as big, you want your storage layer to support operations that are maybe less common for other vendors. In our case, we put huge effort on batch selection, batch insertion, and also introduce sampling as a native operation. So essentially, instead of having an epoch that kind of reshuffles all the IDs for training samples before the first batch within the epoch begins. Instead, every one of the batches natively samples directly from a database. So this way, we don't have to fetch the entire space of keys into main memory. So the next thing that we did, and I've shared it like a couple of months ago, is this tiny library. It's also entirely open source. It's called ucall. So I took a laptop, a MacBook, and I tried to build something with Fast API, and Fast API was surprisingly slow. And everyone has a reason why is that true, or why that is true. And whenever we tell people that Fast API is slow, they keep telling us that that's because of Pydantic, but it's not the only reason. There is a lot more to being fast in modern world, including the part related to I/O. So whenever you have to issue an I/O operation or talk over a network, there are like 3-4 different ways how you can do it. And the same thing for storage. So for storage, you can do a POSIX pread or prewrite system call. You can do stuff like AIO on Linux since early 2000s. You can do memory mapping. Since kernels version 5 and higher, you can do IO-Urang, which some people already kind of are familiar with. And then there is SPDK, and then there is Magnum IO. So there's like 6 ways how to do IO just in the databases, let alone networking. And most of those approaches are relatively new, so it's really hard to adopt them. So what we did here, we took the newest features in IO-Urang for kernels version 5.19 and higher, and we built up a networking library that is just a couple thousand lines of code. It just took a couple of days to build. Today, it implements JSON RPC mainly, but we're expanding it into REST as well. We're also adding TLS support, and the difference is staggering. So on a MacBook with a Core i9 8-core processor, when I ran this script, I got close to 6 millisecond latency, but then I took the ARM C7G instances on AWS. I run a single core server. I got a latency that is 1.2 milliseconds, which is absurd. It's like super slow. And I only squeezed 3,000 requests per second. Then I took this script, I took IO-Urang and the recent Linux kernel, and I got 230,000 requests per second on a single CPU core. So this is a close to 100x performance improvement, and it just took a couple of years to build. Another cool part is that building fast software is nice, but you also want it to be feature-rich. And there are features that are not present in Fast API that we love, that we would love to have actually like in our own code. So the AI that we build is multimodal. So every time we build up an endpoint, we wanted to accept stuff like images or NumPy arrays or be able to return them one way or the other. So every time you try to do something like this with Fast API, you had to manually kind of encode and decode all those complex types. For some of the types, we kind of provided out of the box, including NumPy arrays and pillow images. And this kind of slowly brings us to AI part. So the whole vision was to build up this like super smart, efficient data lake that would work well with unstructured data as well. And when the data is unstructured, you have to have a way to kind of introspect it. So because we work with multimodal data, the go-to approach that everyone knows is CLIP, which is a family of architectures using contrastive losses on top to align vector spaces of multiple transformer encoder towers. And we've used an approach that was developed not far from here at the Salesforce Tower on how to train much more efficient, smaller models. And we kind of improved upon this approach. So instead of training like CLIP, which trained on 400 million samples of data, we trained only on 4 million samples. The resulting network is more application specific, so it doesn't have the same zero-shot capacity as CLIP. But for, let's say, semantic text search similarity or like semantic text similarity, we get higher accuracy on English than CLIP, and on every other language higher than mClip, except for Chinese, which we're working on. The last but not the least, which was also fun to build, is a vector search thing. I know it's a very hot topic today. I love this topic with passion. I've been building vector search engines for a very long part of my life, at least a dozen that I've built in the course of the last 7 to 10 years. The common approach that people use here is to build up an implementation of an algorithm called HNSW, which is hierarchical navigable small world graphs. It has a graph in it, so it's sold. I'm in. What I saw is that there's like a lot of demand for those kind of data structures, and there wasn't anything open source that I would like immediately recommend to people. So I spent another couple of days and I built up a vector search engine. I wrote bindings for it for Python, JavaScript, Rust, and Java. And then I was too tired, so I asked friends to help me. And one of them is now designing a binding for Golang. Another one designed a binding for Wolfram language. And we are adding a bunch of features there as well. So the kinds of operations that are not really common to vector search engines, but we want to have them in to allow like truly scalable solutions. And one of the fun things that we have, and Python developers would probably enjoy it, I really love it, is that you can pass custom metrics. So there is like this layer in between a native implementation and a Python implementation. And whenever data crosses from one part to another, it's always complicated. It's even more complicated most of the time when instructions have to cross from one boundary of the language to another. But there is a way for you to kind of avoid all of this. So let's say you need any kind of general purpose search structure. Uh, for that, you can use this library called usearch. I've actually published an article, and it was on the top of Hacker News, I think, today, called Abusing Vector Search for Texts, Maps, and Chess. So like no matter what kind of objects you store, if you can define a similarity measure for them, this structure would work. But the cool part for Python developers is that if you use something like NumPy that allows you to JIT compile a part of code, you can actually define your custom similarity measure for any kinds of object that you store in NumPy, and then pass the raw pointer of the generated function into the C runtime. And beneath, I'll pick it up, and I'll use it as the function to compare the objects. So those are the 4 libraries that I want to share, all of them optimized for I/O. And they're great companions for all kind of compute optimized libraries. So the way we intend those to be used is actually in conjunction with some of the other libraries I've mentioned here. And just for reference, like on how I/O bound this can be, a fun thing is that like today I was running those vector search benchmarks, and I took a 64-core x86 machine with 128 threads, liquid cooled, like 350 watts of capacity, and I got one number. And then I took a 64-core ARM processor, and I got another number. Who has a guess which one worked faster? No one? Well, you're correct because I didn't give you the information. The information is that the important information is that one of them had DDR4 connected, another one had DDR5 connected. And the ARM processor that actually consumed 2 times less electricity ended up being 3 times faster just because the memory attached to it was a lot faster. So I'll end with this specific example, and I would just tell you that if you have a spare second, go put a star or like check out those libraries. By using them, you'll make a dozen developers on an opposite end of the world very happy. And if you want to join the development, we have a ton of positions. I think the location mentioned in most of them is London, but we are actively considering more offices. Thank you, guys.
Great talk. I think we got a time for like a question or two. Do we have any questions? We got, okay, one there.
Well, there's a lot of space for re-implementing stuff in efficient languages, and I've spent a lot of time on it as well. I personally prefer to stick to C++ because it gives me more access to like bare metal stuff. And oftentimes we have to go beneath it. And I was just discussing the assembly stuff. So like we code in 3 dialects of assembly within my teams, including even like for GPUs. There's a lot of low-level stuff that is not always available in other systems languages. Still, there are also news that actually inspire. So again, we were just discussing a new language called Mojo, like as an extension of Python. I'm really excited to try it out and see like how well it would perform, so that I don't have to rewrite this stuff in C++. I think just being lightweight. So whenever I take a library, I always think like how much of this stuff I'm going to use. So if I'm taking PyTorch, I realize, oh, this is a huge project. Like it's a proper framework. Am I gonna need all of it? If I'm just about to implement something purely like mathematic, I would probably stick to NumPy or CuPy. Or if I need something in between, I would probably stick to JAX, which is like another interesting alternative over here. One more question. Yeah. Yeah, sure. So the way we run benchmarks is relatively broad. So we run internal and we run on cloud. Internal, we have our own supercomputer with 3 types of networking in it, gigabit, 10 gigabit, and 200 gigabit InfiniBand as well. We generally test on all 3 of those. When we test on the cloud, we take both ARM and x86 machines. We generally measure 3 metrics, which would be latency, throughput, and also bandwidth. So latency, the smaller the better. It's like you have just one server thread and one client. You ping and you wait for a pong until you send the next ping. The less time passes, the better. So if those 40 microseconds is actually for the Python layer. In the C layer, we can get down to 22 microseconds with IOURang. So Python adds a bit of latency. Then for throughput, you would measure the number of requests per second that can be handled by a server with an increasing number of clients. So we take multiple setups when clients run on the same server or over network, but in the same virtual subnetwork and very close in proximity to each other. A common case would be taking, let's say, 32 separate machines for clients and just one server, and on it running just a single server thread. And with one server thread, we got to this like 230, 240,000 requests per second. And then the last but not the least is the bandwidth. Once you make messages really fat, what's the overall size that you can process within a second? And within this library, we have like 2 core components that make it fast. The first one is that we use IOURang for kernel bypass. And the second one is every one of the dependencies that we take is SIMD based. So SIMD is like single instruction, multiple data. It's like this big family of instructions. Essentially, like it's just a common term for all kinds of such instructions across all kinds of instruction sets. So all the 4 dependencies that this library has have acceleration for SIMD. This essentially means that the larger the packets, the faster the system works. And even now adding TLS, it's not on the main branch yet, but the numbers look really compelling. So this can be actually one of the faster implementations of RPC for the TCP/IP stack. But for the next versions and like for the internal libraries, we don't really use TCP/IP stack. We just have our own UDP-based networking stack.
Great. All right, thank you. Again, thanks for Ash.